Okay, good morning, everyone. We're going to get started today. Sorry to wake you up. We're going to get started with this morning's plenary session from Professor Francesca Iacopi from the University of Technology, Sydney. So before she gets started, I'll give a little intro. The one thing I'll get on a soapbox. So I've known Francesca for 10 years. We've collaborated. We've become good friends. And I think that's one thing I want to recommend to the folks here, these in-person venues. It's really good not only for your career, but also to develop like lifelong lasting friendships with folks. And it's beyond, collaborations in some senses. And I think we saw that with the first plenary on Sunday night, Matt Terrell. So he has touched a large number of people's lives in his research field, and they've honored him with a guest symposium because of that. So beyond the research, like I said, so Francesca and I, we've hosted each other at each other's complexes, extended that to family and friends. And so yesterday we had dinner with her husband James, and my father was there, and we relived some of our, kind of life experiences that we've had throughout the world at some pretty, magnificent places like here in Cancun. So just recall that IMRC is a great event to develop those long-lasting and, kind of career-developing collaborations. So on to Francesca. So Francesca's an award-winning scientist from Australia, University of Technology, Sydney. She's had a 20-year career, about half in the industry of semiconductors and then half in academic research in semiconductors. It all started back when she went to, I have some notes here because some of these locations are odd to me, but she went to, she got her physics degree at the University of Rome in 1996. She then moved to Belgium and studied in the electrical engineering and material science department. She got her PhD from the Catholic University of Louvain in Belgium there. And then she began a career at the Inter-University Microelectronics Center there, where she became initially a staff researcher and then worked her way up over a decade-long career to a senior researcher. There she studied interconnects and nanotechnology for the semiconductor industry. After about 10 years there, like I said, she moved on to more starting her academic interest, and she got a guest professorship at the University of Tokyo in Japan. And there she studied cryogenics and supercritical fluid plasmas for use in the semiconductor industry. Before going full academic, she returned back to the US at one of the world's largest foundries, global foundries, where she was the manager of packaging technology. So then, after a short stint there, she moved on to her true academic career at Griffith University in Brisbane, Australia. She was awarded a future fellowship by the Australian Research Council, so that's kind of like their basic science funding agency. And she was able, because of that funding, to have time and money to develop a group where she invented a technology of graphene on silicon. And you'll hear a lot of details about that in her talk today. Then in 2016, she moved on to the University of Technology in Sydney. She's a full professor there, runs the Integrated Nanosystems Research Lab. She was head of discipline in the Electronics and Communications Department. She's an elected member of the Board of Governors for IEEE Electron Device Society and is chair and started a chapter there in Sydney. She's also the chief investigator and chair of industry liaisons for the ARC Center of Excellence there in Sydney on transformational meta-optical systems. So she has published over 150 peer-reviewed papers and has 10 US patents in semiconductor technology. So without further ado, I'll welcome Francesca to give her plenary on epitaxial graphene on silicon carbide on silicon towards an integrated future. So.
Thanks. Good morning, and thanks to John for a nice introduction. And again, of course, I would like also to thank all of the organizers and the chairs of IMRC this year for this nice invitation. So John has talked a little bit about my background. So I'm half Australian, half Italian, so I've got a little bit of an Australian accent. And most of my academic career, and so the work that I'm going to talk to you about is the work that I've been leading down under. So as already, so first of all, maybe let's give a short introduction about, I don't know how many of you have been actually in Sydney, Australia. It's a very nice place, as you can see here. And we are lucky enough to be actually centrally placed really in downtown Sydney. So we have a very urban campus. It's a new university, but very well ranked and with a lot of strength, particularly in the electronics area. I have to thank a lot of people for the work I will touch upon today. I might have forgotten a few ones, but these are certainly the ones that we've been interacting. So my group, alumni and present members. John, as he said, has been a very, very important collaborator for us to get started on this work. And he's been mentoring quite a lot of my students. So actually, my students have been going to Dayton, Ohio to actually work with him and his team, which has been really good for them. Also, a lot of funding agencies. Some are Australians, of course. The ERC is our main funding agency. DST is our Defense Science and Technology group, so we work a lot with defense. A lot of the applications that we'll talk about are actually defense related. And our basic research has been supported a lot by the US DoD as well, as actually John has already talked about before. So this is an outline. I don't know, I can talk for hours, so I'll keep an eye to the, I know that I stand between here and your lunch, so I'll try to keep to the time as much as possible. I'll give you an idea about this new technology that we have started about 10 years ago. And look, 10 years is actually probably very, very standard in order to start a completely new technology, because there's so many challenges that come up as you progress. And all of those challenges have to be understood and solved. And now we are really in a very galvanizing phase, because we are moving on into the applications. And that's where we really are getting so excited, because graphene is such a fantastic material, right? But people, of course, would like to know right now, okay, after those many years that we've been talking about graphene, what can we do with it? And so I'll give you a few ideas about the areas that we are, with our graphene, getting into. Particularly in optics and metamaterials. Energy, I'll touch upon that. Biosensing for sure. I don't think I will get to this one. It will be, so I'll give you a few highlights. But before I do that, I will have to introduce a little bit the whole platform. So I'll have to spend some time on this just to, for you to understand where we're coming from. And of course, a lot of this research, because half of my career has been in industry, R&D, has been informed by what I learned working in semiconductor industry. So as I said, graphene, of course, has been out now for quite a long time. It's the oldest 2D material. And we know a lot about graphene, but there's still a lot we don't know. And I'll get to that in a minute. Nevertheless, if we consider the ideal situation of ideal graphene, we know that the ideal graphene would have really very interesting properties that could augment graphene, silicon functionalities pretty in a very impactful way. For example, interconnects, energy storage, photonics, sensing, thermal management, and such and such. And where I'm coming from is the fact that, so we have been focusing on to growing graphene on wafers, on silicon wafers, silicon substrates. And the reason is that silicon has been around for such a long time that we know very well how to make miniaturized systems into silicon. And particularly now with the advanced packaging that allows for 3D stacking or 2.5D, so the interposer and such, there's so much more opportunities to use a 2D material that is grown directly onto silicon. All right, so a couple of preambles. So many of you will be very familiar with graphene, of course, already. And as I said, graphene starts being an older 2D material because it's been around for a while. And nevertheless, it doesn't cease to surprise us. The reason is that 2D materials is the first time, is the first era, basically, that we're starting to deal with 2D materials. And when you start integrating them, there's a whole host of different phenomena that happen, and one has to understand. Well, last but not least, another thing that came up really quite recently is the tristronics, and there's a lot of new research happening in that field. This is quite a controversial article that I like showing, just because to indicate the fact that indeed we don't necessarily understand everything about graphene. We know that certain combinations are favorable, certain others are less favorable, but there is not a unifying theory yet about. There's pieces, bits and pieces, but we have to build the whole picture still. All right, and last but not least is the nomenclature and the language. We are all material scientists, and so we come all from different walks of life. I'm a physicist, a lot of you are chemists, some others are engineers, and we have our own set of nomenclatures and understanding, but we still have to work a lot together. So that's where sometimes we get a little bit into, we need to make sure that we all talk about the same thing with the same names. So what graphene means to a chemist is not necessarily what it means to a physicist and what it means to an engineer. And often, well, the physicists have led the field for a long time. And often what people understand with graphene is just like a thin carbon layer in vacuum, freestanding, not interacting anything around it. And as you can understand, of course, this is a very ideal situation, particularly if you want to harness graphene and use it in integrated systems where, of course, it's going to be surrounded by different materials, having different types of interaction and such. So this is a very important point, very important preamble I wanted to make. Coming from semiconductor industry, of course, I was worried a lot about this. So graphene can really help us in quite a lot of different areas. Not necessarily CMOS, but other areas I think is going to be really important. But how can we bridge that gap between the flakes or the transfer system to covering wafers at the wafer scale that are as big as sometimes 300 millimeters? And then even if you could do it, because people can do it indeed, but how can you actually fabricate devices at the wafer scale in semiconductor environments when you just have a flake sitting on top of the wafer? That's another important thing. And that's why we have started really focusing. There has to be an epitaxial way that is workable for us to use in semiconductors. And a lot of work had been done already in the epitaxial growth of graphene on silicon carbide wafers, so hexagonal silicon carbide. These were early examples from quite a lot of leading groups around the world, and quite a lot is known about how this growth goes. It goes through a buffer layer and then forms a quasi-freestanding layer of graphene on top. It can happen indeed at a wafer scale, but you need to use silicon carbide wafers. And remember, we really wanted to have this on silicon. So what impedes this from being transferred to silicon? Unfortunately, a lot of things. Last but not least, the fact that you can epitaxially grow silicon carbide on silicon, but unfortunately, the lattice mismatch is such, more than 20%, that if you do a TEM section, you will find that the layer is absolutely very, very defective, as you can see here. And of course, if you start with a defective template, your epitaxial growth is going to have to deal with those defects. And all that you will obtain is a very defective graphene, and possibly not even a continuous type of graphene. So that is number one challenge. Number two challenge is the temperature. So that sublimation or thermal decomposition of silicon carbide works best at around 1500 and above. Of course, if we're working with silicon carbide with silicon wafers, we have to be safely below 1400, 1440. So this is not something that we can reasonably reach without creating other problems. So that's another challenge. And there's more than that. This interface is extremely challenging. And this is something, so we not always only had to think about how to solve the challenge of growing the graphene, but also what to do with this interface here. And just hold that thought, because I will get back to that towards the end of this presentation. But if you're able to do that, there's a lot of gain to be had. Why is this? Because you can have site-selective growth, and I'll show you in a minute, because you're still relying on the solid source given by the silicon carbide. You can have potentially higher adhesion, and I'll talk about that. And then particularly, the combination of silicon carbide and graphene is really very beneficial. I will show you some examples for the metamaterials, or I will show you some of the examples also for the MEMS and the biosensing. So what did we decide to do? This is where we came in. And from my previous experience with nanowires, we were working a lot with catalysts. Catalysts always help, as you know. However, here we had to use a little bit of a more complicated trick than just using catalysts by themselves. Nickel, of course, is known to, nickel in contact with silicon carbide forms silicides. So it helps basically to lower the temperature which you can release the carbon and try and use it for the graphitization of the system. However, nickel alone doesn't really work well. And you can see that from here, from this, so here is basically ID over AG's indication of how much defects are in that layer of graphene versus, you see the thickness of the layer. And you can see that nickel tends to have a lot of defects. So nickel alone had been used before, but it wasn't that attractive. Then this trick had been used before for semiconductor nanowires or even for carbon nanotubes. We thought, okay, how about alloying the catalyst with another catalyst so that we have two knobs? And that works beautifully, because by combining nickel and copper, which alloy very well, we have one knob, which is the nickel, to release. With the nickel, we control how much carbon we release from the silicon carbide underneath. And with the copper, we control the graphitization. Not only that, but there is a secondary, not secondary, actually, is as important effect, is that all of that, we do that at 1100 degrees, so much lower than the 1400, 1500 and such. But at that temperature, copper and the silicides are in liquid form. So that's beautiful, because in that case, you're doing a sort of liquid phase epitaxial growth. And it is known to work much better, especially in presence of defects, because you will have a much longer diffusion length for the atoms that are trying to find their best position in the lattice. So that actually releases a lot of the restraints from, it doesn't eliminate, okay? But it releases a lot of the restraints that are coming from the defect on the silicon carbide. And you can see here, we go from nickel only up to here, 1 ID over Ig, so really high, down to here, 0.2, which is not perfect, but this is the difference between a continuous graphene with reasonable grain size at about 100 nanometers, which I'll show you what that does, with something that is patchy and doesn't do much at all, okay? So that's a good start, but the other, so we did, of course, a lot of characterization along the years. Soft-Tech rays has really helped a lot also to understand, thicknesses, and the fact also, clarify also the fact that we have some oxidation just underneath the graphene. So interesting thing is that we grow the graphene directly on the silicon carbide. The catalyst can be removed because they are in liquid phase, we remove that by etching in wet etching and sonication. But underneath, we have some oxidation of silicon carbide. So this will come back. I'll show you later. The appealing thing of the platform, as I said, is that it's site selective, meaning we know how to dry etch and pre-pattern the silicon carbide, which is the source for the carbon, on the wafer level through lithography and etching. And then we can just deposit the layers of catalyst as a blanket layer that covers the whole surface of the wafer. And automatically, what will happen is that where you have the source of carbon, you will have graphitization. But everywhere else, where you have only the silicon, that you will have silicidation, and the silicides we are able to remove. And actually, when we remove the silicide, which is with sonication and wet etching, the graphene stays very adheres very, very well to the silicon carbide. So it stays there, which is beautiful. And so after that, we are able to go ahead with the rest of the fabrication. And this was our early example where we did a wafer level demonstration of patterning of graphene on silicon carbide on silicon. These were MEMS, like bridges suspended on the silicon here. And you can clearly see that here you have, wherever this is colored in like light color, this is basically the part that is silicon carbide and graphene on top, and everywhere else is just silicon, so there's nothing, no carbon there. And the very interesting part of this is that you can do that directly at wafer level by pre-patterning the silicon carbide, and really there is a very good chance to introduce this into semiconductor processes. The same thing can, I won't press too much on this, but the same trick can be used to do graphitize silicon carbide nanowires. In this case, it was a very, very messy forest that we got from collaborators, but we wanted to prove the point, and it proceeds by the same way. And again, we have a very thin, few nanometers oxide, silicon oxycarbide in between the graphene and the silicon carbide core, which is very interesting optically speaking. So we don't need to cover all of the sides of our structures or anything like that. We are helped by the fact that we are working in a liquid phase state. So everything will flow, will cover automatically, which is great. Coming back to adhesion, graphene is a 2D material. So the ideal 2D material would have no bonding in the Z direction, would only interact by van der Waals forces. Van der Waals forces in engineering terms correspond to more or less this type of adhesion energy in terms of joules per meter square. So roughly between 1 and 2. If this number doesn't tell you much, just remember that graphene can be exfoliated, right? So it means that you can easily take it away from the substrate underneath and place it somewhere else. You have some work to do with the modulus, and so to bend it, but that's more or less the value. So now what happens is that, imagine in semiconductor industry, if you want to integrate graphene, you will have to go through hundreds of steps, where each step will be a new deposition, perhaps chemical mechanical polishing, perhaps a lot of different things. And all of those are going to put a thermal and a mechanical load on the wafer. And what typically happens with this type of adhesion energy is that it's going to fail. So at the fabrication stage, we're not even talking about reliability yet. We're just talking about fabrication. Now, it turns out, remember that this graphene that I'm talking to you about has smaller grain size. So about 100 nanometers, judging by the 0.2 figure. And we measure the adhesion on our samples, and that's about almost 3 times as high. So basically, our model is that around the boundaries of the grains, we do have some bonding around, of course. So the grains are clean, but around those 100 nanometer boundaries, we do have some bonding with the substrate. So which is basically a sweet spot, because we can work in integration with 6 joules per meter square. Now, of course, the mobility is something different. Well, I'm going to already make a disclaimer. We're not working on applications where you have to use mobility, clearly. But there's a lot of other very interesting areas that you can look into. And I'll show you a few of them. Before I get to that, though, I needed to make a point about the conductivity, because clearly this is one of the areas where one of the properties that one wants to use about graphene, the really high conductivity. And it turns out, actually the next one explains that even better, it turns out that our conductivity is pretty much in the same ballpark as the epitaxial graphene on silicon carbide ingots, wafers. So the ones that have actually microns large grain sizes. Now, for those of you who are not familiar, so graphene, supported graphene has a typical power relation between mobility and sheet carrier density. So of course they are connected, they don't change independently. And so what happens is that they would appear on a log scale like a straight line. And all of those points that correspond to a straight line, they correspond to roughly the same sheet resistance. Now what happens, of course, is that you have higher mobility for lower sheet carrier density and vice versa. So the higher carrier density, the lower mobility and such. Now the interesting part here is that we have superimposed some of our numbers we were using quite big samples, so 1 by 1. So we're really looking at large scale as much as possible. So these are graphene samples grown on our 111 phase, and these are graphene samples grown on the 100 phase of silicon carbide on silicon. And these are numbers that come from literature from collaborators that have been taken onto epitaxial graphene on silicon carbide wafers, so the hexagonal ones with large grain sizes. And you can see that we sit exactly on the same line, pretty much. And which is surprising in hindsight because this was a completely independent work, but not surprising because we're talking about graphene. So that's that confirms that we're talking about graphene, basically. So this is really important also because graphene, as you know, doesn't have doping per se unless you do something specific. But graphene is basically dependent on charge transfer doping. And the charge transfer typically happens at the interface. So basically what's happening here is that we are interface dominated, not grain size, in terms of conductivity, not in terms of mobility, and which is really important to know. And actually we understood also why we have that different distribution between working on the 111 phase versus the 100. It is because actually that oxidation that I talked to you about before comes back into play here because the tip basically of the silicon carbide is oxidized. And consequently, by graphene being exposed to that, there will be charge transfer, and it will be positive, so it will be p-type. And indeed, all of the measurements have always confirmed that at least the majority of the charge that we found in graphene is p-type. So it comes from this oxidation at the top of the silicon carbide that we create. Why is that different between these two phases? Is because on the 111, we actually can create a buffer layer. Remember that the 111 phase of the cubic silicon carbide corresponds basically on the hexagonal of the 0001, and they respond more or less in the same way, the same chemical situation. So we do form a buffer layer there. So this acts a little bit as a screening. It means although we have oxidation here, this is slightly screened by this buffer layer onto the graphene. It means that we have slightly lower charge transfer, charge carrier density in this case, as the measurements have shown. All right, so this was all the preamble. So now I'll have to go into some of the applications. And as I said, apologies if I have to be a little bit quick. Very happy to talk to you after the presentation if you want to know more details about the different applications I'm going to talk about. So this is something that we have started doing relatively recently. It is extremely promising, and it's about metasurfaces in the mid-infrared. And this is one area where that combination I was talking about, not just the graphene, but graphene and silicon carbide, is of particular interest. Before doing that, I just wanted to introduce this, our Center of Excellence for Transformative Meta-Optical Systems, led by Dragomir Neshev, who is, oh gosh, I can't find Dragomir here. So some of you may know some some of those people, maybe Jagadish and so. So we are 15 CIs of different across Australia, all focusing on to miniaturizing optics. So I worked a lot on miniaturizing electronics, but the optics has lagged a little bit, and metamaterials offer a unique opportunity to do that. And that's also where, again, graphene could offer a lot of opportunities also for in situ reconfigurable sort of devices. And so we're really focusing here in mid-infrared, at least in our group, because this combination of graphene and silicon carbide is really active in that range. I'll show you in a minute. What is the attraction of mid-infrared? It's actually becoming more and more attractive because there's a lot of things that can be done in that range. First of all, you can get some extent of distances, some information about chemical compositions of the molecules that have fingerprints in that range. And I'll show you a very nice example that you probably have all seen already in a moment. And then also for imaging and detection, so LiDAR sort of systems. So remember that when you are looking at using, for example, LiDAR-based, so laser-based radar, you want to stay away as much as possible from visible light. The reason is that visible light has a very, very low threshold for being eye safe. However, in the infrared, you can go a lot more. You can pump much more power. So there's a lot of, and then thermal imaging, of course, thermal imaging. And by the way, talking about thermal imaging, I'm sure you've seen that. This is a beautiful example of what thermal imaging can do. So this is the James Webb Telescope pictures recently released by NASA, where show you exactly what I was saying before, that you can have an idea of the chemical composition of the atmosphere of faraway stars and galaxies just by using IR light. And then, of course, MIR also gives you a different perspective with respect compared to NIR. For example, this was a particularly really interesting example where in NIR, so the system has both, it's complementary. NIR, you could see, for example, in the center of this nebula, just one single dot. But when you go into MIR, you actually can resolve two. And you can see also if you put the right filters, that one is much older. One star is much older than the other. So there's a lot of things that are really important that can be done in MIR. One of the problems is that most MIR systems have to be cooled down, and so they're bulky and such. So we're working towards making that much smaller and portable. How are we doing that? Well, actually, we count on a combination of surface plasmon, which is supported by graphene, and surface phonon, which is supported by silicon carbide. Silicon carbide has a covalent bond, so like a spring mass here. And it turns out that the silicon carbide responds the rest-Allen band, where it behaves basically as a metal, silicon carbide, is in this region between LO and TO, and that's exactly in MIR, basically. Now, our collaborator, Josh Caldwell, had already done a lot of work here using silicon carbide ingots. And he had shown already that actually the polaritonics so basically the phonon, surface phonon in the silicon carbide is particularly interesting because it is a low loss system. So a lot of the plasmonics works really well and works really well at visible light, but it has a lot of losses. And this is a chance for potentially have really, really low loss systems with the silicon carbide. Drawback is that we are just constrained in this very, very specific window in the MIR, and there's no real way that we can change that. However, that's where the graphene comes in. What happens is that you can actually hybridize the plasmon from the graphene and the surface phonon from the silicon carbide. And at that point, once you have that, and this is just the back of the envelope calculation just to give you some idea of the ballpark, you can actually extend, once you have hybridized the particle, extend the responsivity range, not only extend it, but also tune it. by tuning the carrier concentration in the graphene. And this is extremely interesting because of tunability, of course, that's the holy grail, but also the fact that you can extend that responsivity range beyond just the range of the silicon carbide. And this is basically the point we're working on. And you can see it also depending on the charge concentration, you might have more or less correspondence with the matching of the momentum between, for example, a photon in a free space and your material system. So there's a lot of things that can be, that they will have to be considered, but this is really, really promising. And we have started working, so basically the whole thing is understanding, building a very good model for our system and applying that model to design, basically top-down, certain types of meta surfaces. And then we have already looked at quite a lot of different structures. So the beauty of the system is that it allows us to do a lot of different structures with no problems at all. We just have to pre-pattern the silicon carbide, and then the graphene will just coat around. So we worked with nanowires, as you saw before, and this is like a very good example, actually. So this curve here, the blue one, is the example where you have nanowires made of silicon carbide only, no graphene. And so you have the TO, yeah, that's always there. And then you have the phonon here within the Raystrahlen band, but you can see that the absorption is really slow, really small, and also is restricted in that band, as I said before. Now, interesting thing is that when you couple that with the graphene, so when you cover that nanowire with graphene, all of a sudden what happens is that this mode splits because of the coupling. So we have an M1 and M2, but not only splits, it extends outside of the Raystrahlen band, which is the colored part here, and it has higher absorption in the AR, which is really, really interesting. Because also notice that what happens is that when we go from here to there, we lose a lot of the carbon because we are using the carbon to make graphene. So we have less material, not more, but we have much more absorption. And last but not least, we have a lot of we concentrate the field, particularly for M1, into that low refractive index, low kind of intermediate layer in between the graphene and the silicon carbide core. So this is really extremely interesting in terms of enhancing IR absorption with this system. We looked also in nanoparticle. We can play the same game with nanoparticle. We haven't made the nanoparticle, but we wanted to see whether that holds as well. And actually, we had also demonstrated there with a nanoparticle that if you have a silicon carbide core and graphene shell, you can actually increase the absorption in the IR. And this is really interesting in case you want to apply this, for example, to nanomedicine or things like that, because if you want to work in the IR, you won't be the metal particles won't be that performing. Whereas the silicon carbide the system will be much more performing. So the particles will have to be much bigger, and then you have a limit to what you can metabolize inside the body. So this is it also opens another interesting part of work. And then we're working on microgratings, again, made of silicon carbide, covered by graphene, and microgratings for different types of filters. In this case, we are looking about phase imaging. So just to manipulate the numerical aperture of a system directly with using the physical filter. So these are some of the most important areas that we're working at the moment. And yeah, this is all available thanks to the fact that this platform is very versatile. So you can imagine that if you had to make any of this complicated structure by transferring, also because these are 3D, they're not just flat, you can't just put it on top of it. And they have high adhesion as well. So that's, at the moment, this is one of the most straightforward ways of making that, and it gives you a lot of liberty. And then, of course, long-term goal is to work on the dynamic tuning of the system. So yeah, at the moment, we're really focusing on a couple of areas, which is one, devising through the modeling an array of filters of different types, for polarization, for phase contrast, for you name it, all in the MIR that we can use directly in an imaging system. That would be highly efficient. And then the other part that is also very interesting, of course, is the SIRA, the chemical sensing. So I think that if you've been to the first plenary session, Professor Marsan, he talked about surface-enhanced Raman. Similar approach in this case, but we're focusing onto IR, so surface-enhanced IR absorption. So that's another way, another area that we're working a lot on that. And I will have to stop here on this because I don't have a lot of time. I do want to give you some ideas about the other areas that we're working on, particularly more the electrochemical side, integrated supercaps. And here, what we've been doing, so supercaps, so non-Faraday reaction, purely physical separation of ions, and using silicon carbide, graphene and silicon carbide as electrode for the supercaps. We use a little bit of a tweak of that. In this case, actually, the problem is quite different from what I showed you before. Here, we want a very large surface area. That's what we want. We need the system to interact with the electrolyte as much as possible. So we want to make it really rough and effective. And how we do it, in this case, we only use nickel, and we just repeat until we have a full coverage. Also, we found out that the best behavior was when we made quite a few layers, so 5, 6 layers of graphene, all with a certain type of edge defect that allows. So here, in this case, the problem is very different because what we want to have as much capacity for the ions to intercalate the system. So if graphene was just a full, a completely ideal layer with no openings, this would be really hard to make. It would be very slow. But this is very efficient, so quite a lot of layers with a lot of edge defects. Then we find also a way to trick it. Remember that we had this 100 nanometer small, and probably here much smaller, here definitely much smaller grain size. It turns out that that grain size can be easily functionalized, but here, just in presence of water. So what happens is that you attach, for example, OH groups when in presence of water, and what does that is that it makes the system very hydrophilic. And at that point, what happens is that you can even improve the intercalation further than with a system that is more hydrophobic, like no plain graphene. And so we showed that we could do that in situ, and also I won't enter into the detail where we can create also some Faraday, some redox reactions in addition. So we can actually go from, not fantastic performance to a 3 times higher performance. So I won't talk about that. This is just to show you that in this case, it's good to have a lot of defects, because the more defects you have, and the more this effect will be important. So this is also something that I wanted to mention, because a lot of people focus on quality of graphene, meaning defect-free. Well, the really key thing, particularly if you're talking about applications like electrochemistry, is that you want to have defect engineering. You want to have defects, but you want to have the type of defects where you want and the type you're looking for. But ideal graphene won't give you necessarily the right type of results. I'll go just very quickly here. We noticed something really interesting by coupling MOS2 onto graphene, so growing MOS2 onto graphene on silicon carbon on silicon, that we could have this quite interesting effect of growing the crystals of MOS2 almost all vertical with respect to if we had done that, for example, with silicon carbide, which was also quite interesting in terms of behavior. So so the idea, of course, is that we can make electrodes, planar electrodes, and integrate this as a tile of those 3D system approach. Now, we learned a lot when we actually did this supercap work, fundamentally speaking. And it turns out that some of the learning was very interesting for this other application that I wanted to share with you, which is something quite different. Here we are actually looking at graphene, that system of graphene, as a biointerface, particularly as as an EEG electrode. So this is, I wanted to also thank my colleague Citi Lin down in, at UTS and his group, because we're working together, we are co-CIs. He's an esteemed computer scientist, so he knows everything about understanding the brain waves, what he calls it. And we work with them by developing the sensors to actually have the signal from the brain transformed, decoded as a command to an outside machine. That could be anything that receives electronic commands. And I'll show you we've been working with the defense, the Australian government, so I will show you also a nice video in the end that will give you a context about what we're doing with them. So I don't know how many of you know about EEG, but I mean, it's been around for a while. It works really quite well if you use the clinical type of approach with the wet electrodes, and you have to stay in a hospital or in a clinic for observation. You can't really bring it outside because it wouldn't work. It would dry out and it wouldn't work as well. But this is a very, very powerful technique for doing non-invasive diagnostics. And these are only some of the applications. I didn't list them all. So this has been going on for quite a long time. And if you were able to bring this outside of the clinical setting into everyday life, you can understand what would be the impact into monitoring all of these different states and potentially having an early diagnosis for people when some of these diseases can still have a cure or can be stopped before they become really a major issue. But then the other part that stems from the same EEG interface is also the brain machine, how we can communicate directly from the brain with no peripherals and be able to actually give commands to a machine outside. I'll go very quickly about that. So these are some of the brain waves. So neurons are basically our electrical system. They work with ionic currents. Ionic currents are slow, so these are typical frequencies of those ionic currents. So we're talking about really few hertz. Rarely we're interested above 100 hertz, is usually on the low side. And each of those frequencies range give you some different information about the state of your brain. And when you actually look at this, so we're not doing the Elon Musk implantation just because it's a much more complex sort of thing, and it's something that you can reasonably propose only to people that are actually already sick and are wanting to undergo a surgery to have an implant. Here we want to really have this available for the wider public. But then there is a drawback, is that we have a signal attenuation. The signals are just microvolts, so you have to be extremely, extremely sensitive. There's a lot of attenuation, and also there's a very little spatial resolution because we are at a distance from the cortex. So there's a little bit more complications by reading this outside from EEG rather than from electrocorticography, of course. But there's quite a lot of things that you can still do. Another thing, of course, depending on what you're focusing on, you need to know where to look. Depending on what you're monitoring cognitive state, and then it will be a frontal lobe. You monitor visual, it will be on the back. So basically, this is very well known now in neuroscience, and so people know where to, and also where to put different redundancy in the system. So this is all how it works. Now, the thing that I wanted to focus on from our perspective is the availability of dry sensors. Why is that? Because if dry sensors are available, that's when you really can take the system out of the clinical setting and put it out in the operational, even with the Army, as I'll show you in a moment, but it doesn't have to be just with the Army. It could be for anyone who needs some monitoring of their state or wants to communicate with a machine without any, hands-free. So there's been a lot of work into developing, of course, the gold standard is still the wet sensor, silver chloride. But there's been a lot of effort because in that case, you only have a resistive contact with the skin, with the scalp. If you start with dry sensors, then usually it happens that you start having a very important contribution of a capacitive signal, and then of course distortion and other problems, and higher impedance. So that's been usually the big problem. Now this is where graphene can do something different. Graphene is not a conventional thin film, is a 2D film, and we know we can intercalate graphene. And intercalated graphene can have quite a good stability. So actually what we were able to show is that by using graphene directly in contact, well, first of all, it's biocompatible. Actually biocompatible both graphene and silicon carbide, which is great. So you can keep it for a long time in contact with the skin with no noxious reactions. But then the second thing that we showed is that you can reduce the impedance. It has to be as low as possible to overcome that problem of reading this microvolts type of signal. That is very important. And we were able to show that by keeping our system in contact with the skin, after just a couple of tests, the impedance would reduce enormously. And actually what we're doing, we understood that later, but I'll show you. This is a very, very simple system where we have just a square of that system, so graphene, silicon carbide on silicon. Remember that story of the interface. I won't be able to go into these details, but we know how to make that interface extremely leaky so that it's completely conductive. And so we use that condition, and that means that any signal collected on the top here will be transported throughout the silicon on the backside without any other path, conductive path, additional conductive path. And this is really, really great because it makes the sensor really, really thin compared to the bulky, dry sensor, really compact and resilient, and also quite a much better impedance compared to commercial sensors. Now, what I wanted to say once again is that in this case, if you were going to use a perfect graphene with large grain sizes, it wouldn't be the good choice because that type of graphene is going to be quite hydrophobic. And because of that, that story of the intercalation and the increasing better contact with the skin and a high conductivity as a sensor would not be as good. But because of that, the fact that we have small grain sizes and we can functionalize them in situ, in the presence of water, we basically go from a high contact angle, initially of over 70, down to 30 and something after contact with the skin. And so this is really helping us to achieve stable, very stable. It's absolutely, we kept it for the whole lockdown down in Sydney. We kept the sensors in high saline solution. We maybe lost 1%. It's incredibly resilient in terms of adhesion, but also in terms of electrical behavior, which is something that you can't achieve with this type of sensors. And here you can, even without knowing much about what this all means, these were two sensors, a signal on the frontal cortex. And these are the graphene sensors. These are the pin electrodes, and these are the foam electrodes, so the commercial ones that you see here. And you can see that the quality of the signal that's picked up by the graphene sensors is definitely much more valuable than, for example, well, the foam sensor would be the worst, as you can see here. And impedance is a big part of the story. So, and resilience, of course, is something that our sponsors from the Australian Army are very, very worried about, because if they are out in the field in operation, they want to make sure that if you start sweating a lot in conditions that are clearly not the ideal conditions in a lab, the system will still continue working. So how does it work? I won't have the time to explain you the whole paradigm, but just bear with me, and I think there is some explanation in the video. So it's a visual-based paradigm. Some information is fed on a HoloLens to the soldier. This is this is Damien, who will speak in a little. We work with Damien, so he's wearing a HoloLens, he's wearing sensors on the back, he's wearing a reference graphene electrode here. So at the moment, we don't have it yet on the back because we're developing a system that can go through the hair, unless well, my postdoc actually has volunteered to shave, so he can do that. But basically what's happening is that the stimuli is fed to the user makes the decision is picked up by the visual on the visual cortex, but the sensors transmitted wirelessly to the decoder platform, where there is algorithms working with artificial intelligence to decode the information and send it to the platform. And in this case was this robotic dog from Ghost Robotics that is being used by the army, so that the user can hold weapons in their arms without having to have additional peripherals, and just send the dog ahead of them in order to look for dangerous situations. And maybe I don't know if I can, that's explained.
So the technology that we demonstrated today is called a brain robotic interface, and it's a way of a soldier operator being able to command an autonomous system and use their brain signals. So rather than voice or a command console or any other form of command, we can use an interface via a headset to allow them to move an autonomous system. And today we use the Ghost robots because Rico has had experience with experimentation with this kind of autonomous system. Army absolutely plays a part in the development of this technology beyond the funding, and we have a range of use cases that we're looking to work with a range of stakeholders to ascertain the best way to test this technology and to help de-risk future acquisitions, particularly in the autonomy space.
The control I can exert over the robot is I can tell it to go to a number of, in this case, 6 predetermined locations. You don't have to think anything specific to make the robot operate, but you do need to focus on that flicker. So it's more of a visual concentration rather than having to clear your mind and have mindfulness.
So hopefully you understood a little bit from Damien's explanation of how the system works. And yeah, we're very, very privileged and glad to work with them. So these are real soldiers in the field that are using our system and testing it out and coming back to us with all their list of complaints, but also a list of things that they really liked about it. And particularly Damien was looking forward to have the finalized graphene sensor, because the commercial sensor that he was using on his back was just making him maybe almost scream after a few minutes. So that's a very important thing, that we are able to miniaturize the system and make it also much more friendly in terms of long-term contact. So I won't be going through this. I hope a couple of takeaways is that, it's graphene, we don't know everything about it. We think we know, but there's a lot, and depending on applications, not all type of graphenes work the same way. So you really need to target the graphene to the application you're looking for. And sometimes the effects are good, particularly for electrochemical applications. Particularly about this platform that we have developed over the last 10 years, I hope I have shown you that we have really a lot of versatility and reliability, which is something that is really important in order to scale this up. And then, yes, of course, that the combination of the graphene and the silicon carbide is actually something really important. It's not just the graphene by itself, but a combination of those two materials. And just let me finish by doing some advertising for Spring MRS next year. I'm one of the organizers of this symposium, which will be really focusing on CHIPS Act has finally passed in the US, not just the US, Europe is pushing that a lot. A lot of places around the world are actually understanding how important it is to be independent in terms of making your own technology in-house. And so we'll be working together with MRS and the IEEE Electron Devices Society to bring together both industrial and academic knowledge and R&D in order to work together to accelerate materials into electronic devices. So hope to see quite a few of you over there in San Francisco next year. So thanks for your attention. So I think we've got 5 minutes.
Thank you, Francesca. The paper is open for questions. I think there's microphones around. Okay, I'll kick off with a question. Oh, wait, Norma, go ahead.
Thank you. Very nice presentation. My question is, do you think there is hope to utilize materials that come from sustainable sources like ferrolide or bio oils that can actually be rearranged in a two-dimensional series? And how do you think that can change also the way we think about doing new materials with metals or alloys that can be sometimes not as sustainable as others? Not as sustainable as other materials.
Okay. In terms of, we don't do work in the field of, of biodegradable sort of sources and such, but there's a lot of colleagues out there that do that work. So I know colleagues working on biomass and transformation of that also in graphene. So graphene is carbon, so in principle, if you have an organic source and you have the right conditions, there is hope that you could transform it into some form of graphite carbon. That tends to be, though, usually more the chemical approach to graphene, which is more the bulk approach, and which is great. I mean, there's a lot of applications for that in bulk. Well, even batteries, or even there's a lot of really important applications there. It's not necessarily what we're doing, because here we're really looking at miniaturization, and then using that type of source for miniaturization. I wouldn't say it's impossible. Maybe there is a way, but at the moment I don't see the link directly. Let's say that. But yeah, but it's definitely a very complementary area and very important to look into. Hope that answers your question. Thanks.
Are there any other questions? No, we stand between you and lunch for a little bit. So perhaps if you have a question, we can connect with Francesca after her talk. So I have a certificate for Francesca for her plenary contribution to IMRC. And let's thank Francesca again.